All right, everyone, we're sitting into second period on Thursday, February 11th, and I'm going to go ahead and give a lecture to help you guys review some of the content that you learned last class, and then hopefully we will be able to finally start this worksheet right here, the net ionic equations and half reactions. All right, so I bet none of you guys actually looked at it. I'm looking at these students right now with all their pearly white, beautiful teeth and smiling at me. How many of you guys didn't even look at it? Yep, honesty. Okay, so let's try that. Let's try that now. But before we dive in there, I do want to see if you can do this warm-up first. Okay, so this is a warm-up for the day, and I'm going to review that with you. What you guys have to do is get to the net ionic equation, and net ionic equations are kind of new for you. All right, so I'm going to start slow and go over this first. Okay. All right, so your warm-up, in case you missed it, you're combining sodium with silver chlorate. All right, silver chlorate. Sorry, there you go. Okay. First things first, you got a little bit of experience with the predicting products. You probably want to figure out what kind of reaction you've got first. Once you figure out the kind of reaction you've got, predicting products is easy. Okay. So what kind of reaction you got? Single replacement. How did you know? You got this guy sitting by himself. He's not even in a compound. All right, what do we have to check in order to make sure that single replacement reactions actually work? What do you have to check first? Metal reactivity series. Okay, so if you don't have this one pulled out yet, you definitely want to have this pulled out, okay? Because we're going to be looking at this over and over and over and over. Okay, so sodium is trying to cut in on silver. So on the metal reactivity series, you need to check that sodium is powerful. And sodium is indeed powerful. He's way more powerful than silver. Silver's like way down here. All right, so first things first, this reaction works. Therefore, we can predict our products. Sodium is not going to be alone on the other side. So he's going to be part of a compound, which means you have to balance your charges. Charge of sodium is +1. This is a polyatomic ion. You might want to check his charge. 1. All right, so chlorate is +1. Sodium is -1, so that's perfect. Who's your other product? All by himself. There he is. He's silver. Got popped off. All right, and I do want to make sure that you realize that I just draw charges to help you. But in my final reaction, I erase my charges. Never leave your charges in your final reaction. All right. Is this reaction balanced? Yeah, I was nice. I did all +1, -1 stuff, so I was being kind of nice. All right, so there you go. We check charges. We balance the reaction. How do we get the net ionic equation? We kind of need to check something. I'll give you a hint. Solubility rules. There you go. I was just going to pull this up. So we do need to check our solubility rules, and that will help us get our net ionic equation. So your anion is chlorate. Find your chlorates. Yeah, all chlorates are soluble. Do you see any exceptions? Ooh, that makes it really nice. Okay, your silver chlorate is soluble. Your sodium chlorate is soluble. These are solid metals, just like in the lab when you guys had to stick those chunks of metal in there. All right, so those are solid. All right, so in order to get a net ionic equation, you have to refresh your memory of what happens to ions when they get into water. What happens to ionic compounds when you put them in water, guys? What happens when things that are ionic dissolve? They break up into their ions. They break into ions. So they don't break up into their individual atoms. You need to be careful. So even though if you look at this ionic compound, silver chlorate, the way it'll break up is you'll have silver ions and chlorate ions. And you have to remember that chlorate is polyatomic. So you ready? Anything that says AQ, we break apart. And here's how it'll look. Sodium's solid. He does not break apart. He does not turn into an ion. He is a solid chunk of metal that you're putting into the solution. So leave him solid, no charge. The silver, though, is in solution and it's aqueous. So he is now in his form of an ion. He's an ion floating around in water. So we're going to go like this. We're going to give him a charge, and we're going to label him aqueous. The thing that sucks about this particular unit is you have to pay very close attention to detail. You have to have your charges, and you have to label those aqueuses and solids, and if you forget, it's wrong. So let's go here. You have a polyatomic ion. Let's get him in there. He's chlorate. Notice that I keep the chlorate together. I keep the chlorine with the 3 oxygens because that's what chlorate is. He's a polyatomic ion. And remember, give him a charge, label him as aqueous. All right, let's move on to the product side. On the product side, you have sodium chlorate. Ionic, dissolved. So I'm going to make him turn into his ions. All right, so we have the sodium ion. I think you guys already have that charge kind of memorized. See how I'm labeling AQ on that ion? And the other ion that we have is the chlorate. He's polyatomic. Let's get him hooked up. ClO3. Polyatomic, there we go. Keeping him all together. And then we also have the sodium. Or no, it's not sodium, sorry, silver. And that is a solid chunk of metal, so make sure you label him as solid. Ladies and gentlemen, pretty lengthy, but you have just created something called the total ionic equation. What we need, and what I asked for, is the net ionic equation. What do I need to remove? Spectator ions, and how can we tell what the spectator ions are? How can we tell? They did not change. Good job. So looking at this reaction, which ion did not change, didn't have like a change in the states? Yeah, the chlorate ion is aqueous on both sides, didn't change, he's still aqueous. So your spectator ion is going to be the chlorate. So we've identified our spectator, and if you just cross him off like this, that, whatever's left, is your net ionic equation. You're done. If you want to rewrite it, be my guest, but all you have to do for me is cross off your spectators, and then we're good. All right, that was one of your questions on your warm-up. The other one is looking like this. Magnesium sulfate and potassium carbonate. Magnesium sulfate, potassium carbonate. Magnesium sulfate and potassium carbonate. All right, so this is the second problem on your warm-up. First things first, what type of reaction is this so that you can predict your products? Double replacement, good job. So a double replacement, the guys in the front, the magnesium and the potassium, they switch. But you're making compounds. You must balance your charges. Here we go. Who's magnesium's new buddy? Carbonate. Good job. Check charges. Magnesium, element number 12. What is his charge? +2. This polyatomic ion is on your list. What's his charge? -2. All right, so that's a cool compound. Let's keep going. We've got potassium. Who's his new buddy? Sulfate. Check charges. Potassium's number 19. +1. How about sulfate, polyatomic? -2. Okay, so balance those charges. The thing that confuses a lot of my students when they're doing these problems and they're predicting their products, they see over on the left that you have 2 potassiums, and guess what their instinct tells them to do because they're so used to balancing? Let's use 2 on the right. But what if I didn't have a sulfate? What if instead I had, like, say, phosphate? And phosphate's -3. They'd have the wrong formula. And if you have the wrong formula, you will find it absolutely impossible to balance a chemical reaction. So listen to my advice. If, when you try to balance a chemical reaction, it literally becomes impossible to balance the reaction, check your formulas. You messed up. All right, so remember, I'm never going to give you a reaction that's impossible to balance. All right, so this reaction, is it balanced? Yes or no? Yes? 1 magnesium, 1 magnesium, 1 sulfate, 1 sulfate, 2 potassiums, 2 potassiums, 1 carbonate, 1 carbonate. All right, everything's cool. What do we do now? Well, you need to refresh your memory. What makes double replacement reactions work? The presence of a precipitate. So, yet again, we have to reference our cation and anion sheet with our solubility rules. So on the product side, you made magnesium sulfate. I'm sorry, you made magnesium carbonate and potassium sulfate. So you go back to your solubility rules. Let's check the carbonates. Okay, rules for carbonates. He's down here. They're supposed to be insoluble, but we're going to check for any exceptions. Exception here says alkali metals and ammonium. All right, so carbonates are insoluble unless you have an alkali metal or ammonium. Well, magnesium, not an alkali metal, so guess what you just identified? What is the fancy word for an insoluble product? Precipitate. There's your precipitate. Let's check the other guy. You have potassium in the front. Who's an alkali metal, by the way? Do you remember what I told you if you ever see an alkali metal in the front? Always soluble. That's a nice little thing to remember. And remember this too. Hydrogen, if you ever have like an acid, let's see. Never mind. If you ever have a hydrogen in the front, hydrogen is acting like a metal now for you guys. Remember that. And all acids will be soluble. All of them. It's kind of cool. All right, so this guy right here is soluble. Just label him as an AQ. This reaction works because you created a precipitate. Go back to the reactant side and label up solubility. You can check that on your list if you want, but I'll help you out a little bit. Both of them are soluble. Okay, AQ, AQ. All right, perfect double replacement reaction. Let's get something called the total ionic equation. Now, some of you guys probably are getting good at this. Can you already see who the spectator ions are? Yes, yes, I hope you can. Look at the product side. If he's soluble on the product in a double replacement, if these guys are still soluble, well, those are your spectator ions. Like right there, you can identify them. It's easy to see. Now, guys, it's totally fine on your homework if you want to skip doing the on some homework. No, not on your homework, on your test. Sorry, on your test. If I only ask you, like on the test for the net ionic equation, you will not have to show me the total ionic equation. That's just overkill. All right, like when you come into AP, a lot of the times I tell my students, what's the net ionic equation? And this is all they have, and they can instantly just give me their net ionic equation fast. So if you can see it, do it. But for practice, I'm going to show you the total, just so that you can see what it would look like, okay? All right, so this is just for practice. I'm going to show you the total ionic equation and break everything that says AQ. I'm going to break all of that stuff up. So here, starting off, we've got the magnesium ion. See how I label the charge? Sulfate is polyatomic. Make sure you keep those polyatomic ions together. Now watch this part. How many potassiums are in this compound? How many potassium ions? Because potassium looks like this. It's just K+. How many K pluses do we have? You have 2. How do you show more than one ion? That's a good question, huh? You can either go like this. You can go 2 K+, or you can go K 2+. Which one do you think is accurate? The one on the left. Guys, what did I tell you a subscript means? That it's bonded. This is not correct. All right, so subscripts means that there's a bond. So guys, these ions are free floating. They're roaming around. I don't want to see them bonded up. So instead, I'm going to go like this, 2K+. So if you have more than one ion using a compound, show coefficients. All right, here's my carbonate. See how meticulous I am about showing those charges? All right, this guy's your precipitate. You see how he's solid? He does not break up in water because he's a precipitate. So if he does not break up, you leave him together. There he is. Here's another product here that has 2 potassium ions. How do you show more than one ion again? Coefficient. Don't forget charge, label AQ. You have to have great attention to detail here, okay? Sulfate, polyatomic ion, keep him together. And label him aqueous. Alright, guys, check that out. He's huge. There is your total ionic equation. Do you see your spectator ions now? Cool. Okay, so the potassium stayed aqueous on both sides, so he's one of your spectators. And then the sulfate stayed aqueous on both sides, so there's your other spectator. And you're done. All right, a little practice with net ionic equations is good for your health. All right, everyone, coming back to your class website, we are now going to move on to looking at this worksheet number 4, net ionic equations and half reactions. All right, page number 1 looks like this. And then if you flip over to page number 2, you get a little confused. Hey guys, just understand I was trying to save copies one year, and so I actually made this kind of like a, 2 copies on one page. So just ignore that duplicate right there. In fact, I'll delete it. There you go. See? All right. So here is the front page, and here is the back page. Not very many problems. Let me show you how to do one of them, okay? Let's start with the double replacement. So you're going to want a separate sheet of paper, guys. So grab that. And you see how nice I was? I put the solubility rules and everything right there. Aw, you're welcome. All right, to do these problems, your instructions are located right here for the double replacements. I'm going to read it through. Complete and balance. Write the word. Write the equation. Indicate gaseous products if there are any. Keep going right here. Write the ionic equation and net. Okay, it didn't say total, so we might be able to skip it a little bit, okay? And then it says, if the reaction doesn't take place, you need to indicate the reason. The only reason why a reaction will not take place in this one is if you have all soluble products. All right, so it's going to be pretty important to check those solubility rules. All right, peeps, let's do this. Let's try number 1. Iron 2 bromide and potassium carbonate. All right, question number 1 on the worksheet. So one of the things that they do want us to do is to do the words. So why don't we go ahead and predict our products, and when we get our products, we'll check solubility just to see if it works. So because you had an iron 2 on the left, you will have an iron 2 on the right. Who's iron 2's new buddy? Carbonate. Okay. The other product will be potassium with who? Good job. Potassium with bromide. Okay, so after you predict your products, you may want to just go to your solubility rules and see if this actually works. We're looking for a precipitate. Iron 2 carbonate. We're going to check the rules for carbonates. Okay, it looks like carbonates are insoluble unless you have an alkali metal or ammonium. So let's go back. Do you have an alkali metal or ammonium sitting on your carbonate? No. You just found the solid precipitate. Okay, so that is not soluble. Let's go to the rules for bromides. So bromide. All bromides are soluble except silver, mercury, and lead. So this is soluble unless you have silver, mercury, or lead in the front. And we don't. So that works perfect. Thank you. Okay, you might want to check your reactants while you're at it. All carbonates are soluble or insoluble unless you have an alkali metal. So carbonates are supposed to be insoluble unless you have an alkali metal in the front. And sure enough, potassium is an alkali metal. So this is actually AQ. Let's see, bromides, how did that work again? Can't remember. So soluble unless you have silver, mercury, or lead? Yeah? Okay. So this guy's AQ as well. Yay! Very nice double replacement. Okay, does this reaction work? Beautifully. It works absolutely beautiful. So you do have a precipitate on the product side, so we now can proceed on. You ready? What's the charge of the iron? 2 plus. Oh, wait, I don't want to show my charges right there. What am I thinking? Hold on. Get that out. Okay, I'm going to put the charge underneath so that you can check my work, okay? Bromide is like this. He has a -1 charge. So I'm going to double up the bromine. Potassium's an alkali metal, so he's +1. Carbonate. Check your 8s and ites on your list. He's -2. And I do realize I'm going fast, but that's just because I want to kind of move quickly. Iron 2 will still be a +2. Carbonate, -2. So that's perfect. Potassium is a positive 1. Bromide is a negative 1. All right, so check your formulas, check your charges, check your subscripts and everything. And once you get that done, please understand that I don't like to see charges in your final work. I'm erasing those. Okay? That was just me doing some scratch work on the side. All right, what do you want to do now? What do you balance? Yeah, balancing the reaction would be nice. And what's the other thing we should probably think about doing? Labeling solubility. We'll get to that in just a second. All right, it looks like you have 1 iron, 2 bromines, but over here you only have 1, so I'm going to double that. And we already found the solubility, but I'm going to put them here. All right, so balance and label solubility. Once you balance and label solubility, you can move on to the next part. The next part for us would be finding this is called, right here, what you have is called the ionic equation because you labeled your solubility. This is the ionic equation. Now, can you jump straight from the ionic equation to the net ionic equation? Can you see who the precipitate is? All right, the precipitate's great. This is good. You have a precipitate. Can you identify the spectator ions? Guys, those are aqueous, right? Find them on the reactant side. Is potassium aqueous on the left? Well, yes. Is bromine aqueous on the left? Yes. Those are your spectators. The potassium and the bromine are your spectators. So when I get to I'm going to try to break ions apart. I'm only going to be looking at the iron and the carbonate because they're the only ones that did anything, that changed. Are you ready? Let's start. On the left, here's my iron. He was a positive 2 charge, remember? I'm going to get his charge. Okay. Who else should I keep on the left side, on the reactant side? Look at your precipitate. Who else do I need? Carbonate. Don't forget his charge. Don't forget the AQ. And what did they make? A precipitate. Notice how I keep my precipitates together? No charges. Guess what, guys? Net ionic equation. Done. This reaction is done. This question is done. All right, does that kind of make sense a little bit? Nice. Now listen, I'm just warning you. In some of these problems, you may have an insoluble reactant or 2 insoluble reactants. Does that stop the reaction from working? No. What does that do? Slows it down. So on some of these, I'm just giving you a hint, you may not be able to break anything up and the reaction will still work. All right, so some of them, you don't have to do as much detail. This one, we had a bunch of stuff that was aqueous. All right, so watch out for that. All right, I'm going to switch gears and move on to the bottom half of this, okay? So if you want to, I don't know how big you write. You can do maybe the double replacements on the front side of your paper, but now flip over and we'll do the single replacements on the bottom. Okay, so now we're going to switch gears and move on to the bottom, and I want to show you one where it actually works. Some of these guys, when you start looking, you'll be like, that doesn't work. So, for example, number 1, let's check that out. Aluminum is trying to cut in on zinc. Aluminum is trying to cut in on zinc. Is aluminum more reactive than zinc? Yes or no? Here's aluminum. Yes, he is barely more reactive. So over here, I just recommend you do this. Always check to see if the reaction works. So before I even do anything, I know number 1 works. But why don't you guys check number 2? Does number 2 work? You need zinc to be more reactive than sodium. Is zinc more reactive than sodium? No. So guys, I'm totally saving you like a ton of time, okay? Please, please, please check to see whether or not the reaction works or not before you dive in. So number 1 works, number 2 does not. And the one that I'm actually going to show as a demonstration for today to help you with your homework is not number 1. I want to do number 2. And it says, hint, check the halogens on the periodic table. Chlorine is higher than bromine, so this reaction does work. And I love this one as a demonstration, so this is the one I'm going to show you today, okay? All right. So I'm doing number 3. I'm doing number 3. I'm sorry, I'm making you guys skip, but I'm doing it for good reason. I just know that this one is where I get most of my questions. All right, you guys ready to rock? So same procedure. We still want to do the words. We want to do the formulas. We want to balance it, label solubility, break up the ions, cancel spectators. But then on the bottom half, ladies and gentlemen, and it only is for the bottom half, you're going to have to do half reactions on the bottom. And so that's very new for you guys. There are notes posted. It can be a little confusing, and that's why I want to do this one, okay? All right, so let's predict our products. Cobalt is going to be hooking up with who? Chlorine. Stop. So the chlorine turns into chloride. And then who got the boot? Bromide. Bromide will turn back into what? Bromine. Okay, remember how we go to ide when we make ions? All right, let's do some formulas. This guy is a positive 3 because of that Roman numeral 3. Bromide is -1, so I'm just kind of showing my work again for you. Chlorine is a gas. He cannot stand alone, so we're going to go like that. Double them up. Cobalt is a positive 3. Chlorine is a -1, so I got to go like that. And then bromine gas, diatomic. All right, so I'm just showing my work by showing those charges, but I'm going to erase those. Okay. All right, so there is your bare formula. What would you guys like to do to him? You need to do 2 things. What 2 things do we have to do before we proceed? Balance. Good job. Okay, let's see. 2 chlorines, 3 chlorines. What's a common multiple for 2 and 3? 6. All right, so watch how I do that. All right, so now I've got 6 chlorines. Do you guys see the cobalt? I've got 2 here, but only 1. So I'm going to go like that. Now careful, that'll give me 6 bromines. Come over here. Good job. All right, it's balanced. What next? Solubility. Okay, so check your solubility rules for bromide ions. Okay, let's see. All bromides are soluble except silver, mercury, and lead. We don't have silver, mercury, or lead on these bromides. Sorry, I'm looking at bromide first. That's an AQ. What's the rule for chlorines? I think it's the same, isn't it? So all chlorides are soluble except silver, mercury, and lead. So that's aqueous as well. There you go. You ready? That right there we would call the ionic equation. Now for practice, I'm going to show you the total ionic equation just for practice. I don't know, can you guys tell who the spectator ion is at this point? I can kind of tell. Who is it this time? Cobalt. Cobalt is being lazy, okay? He's not doing anything. He's aqueous on both sides. But I want to show so that you guys can see how to break up ions for practice, so I'm going to do that here. Let me show you what it would be. How many cobalts do you have here? You have 2 with that coefficient in the front. This guy is a positive 3 ion, and he is aqueous. So I broke him apart. You see how I've got charges on him? Now, bromide, the bromide ion is just Br negative. How many bromide ions do you have total with the 2 and the 3? That's right. And he's an ion that is dissolved in water. All right, now this is a gas. Gases, you do not break up, and they have no charge. Remember, only aqueous have charges. So this guy's aqueous. We have 2 cobalts on that guy with the coefficient. How many chloride ions, guys? Chloride ions, how many? Well, you've got 2 in the front. Yeah, I've got 2 cobalts already. So how many chlorides? You have a subscript of 3. Remember, chloride looks like this. It's just Cl minus. How many of those do we have here? 6, a total of 6. And then the gas, leave them alone. scoot over just a little. There, leave them alone, no charge. All right, that is called the total ionic equation. When you remove the spectator, you will make a net ionic equation. You guys are right, cobalt was your spectator ion. I'm removing him. Now here is where we jump into some new content. You were just introduced to this last class, half reactions. Now, I've been told that sometimes I go fast in this section, so if you've got a question, please ask. Do you realize that you have two elements that changed? One of them is bromine, one of them is chlorine. So we have what we call two half reactions because we have two different elements. One of the half reactions involves bromine. Bromine is one of your half reactions. The other half reaction is chlorine. Let me show you. Bromine started as an ion dissolved in water. This is how he looked on the reactant side, and I'm only looking at bromine right now. What happened to bromine? He changed. Go to the product side. What did he change into? A gas. This is the half reaction for bromine. Now there's another half reaction that we have to do for chlorine. On the reactant side, chlorine started as a gas, a diatomic gas. But he changed into 6 ions over here in water. He dissolved in water. These are your two half reactions, one for bromine, one for chlorine. Is everyone following okay? Yeah. So the question was, isn't there supposed to be a coefficient of 2 on what? The first cobalt? Oh, I missed it. Thank you. Yeah, it's a spectator ion, but I'm glad you caught that. Thank you. All right. These half reactions, we need to start off with a couple of concepts here. First of all, I want you to realize when you see half reactions, we are talking about oxidation and reduction. One of these elements was oxidized, the other was reduced. And that is kind of a new topic, so I want to refresh your memory. What is oxidation and what is reduction? Do you remember this? Oil rig. What does this stand for? Oxidation is loss, reduction is gain, right? Another way to think of it, and this was in your notes and you can always refer back, in oxidation, the overall charge will increase. Charge will increase. But in reduction, the charge will decrease. So let's see if we can figure out here what happened. Starting on the left, your bromine ions are a -1 charge each. But it turned into a gas. Do gases have charges? No, they don't. This went from -1 to 0. Think of a number line. Did he go up in value or down in value? He went up in value. Bromine was oxidized. That is an oxidation half reaction. Chlorine. Chlorine started as a gas. Gases don't have a charge. And he turned into an ion. He's negative here. Think of a number line. He went from 0 to negative. Obviously, this guy was reduced. Here's the thing. You will always have oxidation and reduction happening together. You can't have one without the other. I think I mentioned it's kind of like a battery. On a battery, there's a positive terminal and a negative terminal. On the negative, electrons are being pumped out. At the positive, that's where the electrons come in. You can't have loss without gain. You can't have gain without loss of electrons. And it goes one step further. You ready? When you get to this point on your half reactions, the number of electrons are the same. Let me show you what I mean. At the top right here, at the top, this half reaction is not complete until we absolutely, positively Get the charges equal on both sides. And the only way that you can get the charges equal on both sides is by adding electrons. What charge are electrons? This is a review. What charge are electrons, guys? They're negative. They're negative. Negative charge. Electrons are negative. So over here on the left, you have 6 negative ions. That is a total of -6 on the left. On the right, your bromine doesn't have a charge, right? He's 0. The charges on both sides of this half reaction have to be absolutely identical. So if it's -6 on the left and 0 on the right, you can do one of two things. You can make both sides -6, or you can make both sides 0. But you have to add electrons. What charge are electrons, guys? Negative. So if I add more negative to the left, that's not going to make both charges equal. The only way that this will work is if we add 6 electrons to the right. If I add 6 electrons to the right, remember the only thing that you can add are electrons, okay? You can't add protons, although I wish we could. You can't do that. If I add 6 electrons to the right side, that will give me a -6 charge with that bromine gas, right? Does everybody see now that the charges are absolutely identical? You have a -6 on the left and a -6 on the right. This half reaction is ready to go. This is perfect. Now let's get this guy to be absolutely perfect. Down here you have 6 negative ions. That gives you a -6 charge. Where are you going to put the electrons this time? On the left. So I'm going to come over here, and I kind of didn't give myself room. Sorry, hold on. Okay. So I'm going to come over here to the left, and I'm going to add 6 electrons this time to the left. Here's the beauty for me. I like this part. Oxidation reduction. The electrons will always be on opposite sides of the two half reactions. Do you see how on the top we have electrons on the right and on the bottom we have electrons on the left? That's not only the only thing that you will always see. You will always see the electrons on the opposite side and the same number of electrons on opposite sides. If you have 6 on the top, you have to have 6 on the bottom. If I throw out 6 electrons, I need something to catch all 6. Otherwise the reaction doesn't work. All right, does everybody kind of get a feel for this? It's very difficult when you first start. Please dive in and learn this for yourself. You will struggle, but when you struggle, just realize that that's a learning process. Go back to your notes. Go back to this video if you need to. Go back to this process. The process will always be the same. And as long as you understand the process, you'll understand the overall thing that you're trying to do. All right, guys, I'm going to stop the podcast at this point. Dive into your homework. You also have another worksheet posted, but I think this is a tough topic. The other worksheet that we're supposed to work on is the all reactions worksheet. When you come back to the class website, it's right here. I'm not sure that we're going to have enough time for it. And honestly, I'm okay with that. This process in this unit, you have to be able to learn this process, and it takes time. All right, guys, priority number 1, go back to this guy, the net ionic equations. I want you to work on that. And then priority number 2, if you have enough time, go ahead and start the all reactions. But I'd like that net ionic equation done by next class. We'll see how it goes. We'll probably have to review, I'm sure. All right, guys, stopping now. Take care.